So we're going to start recording here. And, where'd you go? There you are. All right. Now, last time we left off on boiling and vapor pressures. So when we're boiling something, what's happening is we have increased the vapor pressure, the pressure of the vapor over that liquid, up to the atmospheric pressure. Okay. And because the vapor pressure is now the same as the atmospheric pressure, that atmosphere that used to be pushing down and holding those molecules down in that liquid is no longer doing that, is it? It's now at an equilibrium where it's getting pushed back by the vapor pressure. Okay? And so that's why then boiling happens, where you get the gas molecules on the bottom usually where you have your heat, but it doesn't have to be in the bottom. If you heated the sidewalls, it'd be outside. And those are going to then bubble up and escape, right? Which is what we call boiling, okay? And so again, remember that it is where the vapor pressure is equal to the external pressure that's being applied, i.e. usually the atmospheric pressure. Okay, so each liquid molecule must also overcome several forces. So what we have in a liquid is we have attractive forces that are happening between its neighbor molecules and that molecule that's going to try to escape. Okay, you can think of this a bit like the gravity of Earth, right? And so whenever you boil something, you break those connections and then it launches out and escapes. And that's where it goes to a gas. Okay. When you've reached the boiling point, the molecules are going to have enough energy on average to escape and go from the liquid to the gas, thus breaking those connections. And so that's actually what your boiling point ends up being. It's another definition of your boiling point is it is where you have an average kinetic energy that allows for a lot of these molecules to escape, okay, to break their connections. So again, the boiling point, temperature at which the vapor pressure liquid equals the atmospheric pressure. That's usually the best definition and the most useful one. So the types of attractive forces, what sorts of forces are keeping these molecules together? You'll notice that this is highly related to the lab we just did for some of you and are going to be doing today for others of you, okay? And so the attractive forces are going to be caused by the electron-rich area of one compound being attracted to the electron-poor area of another compound. Okay, this is the overall what causes attractive forces. So every molecule has some magnetic properties. You guys may remember polar versus nonpolar that we did before, right? Okay, so polar is a great example of this. We're actually going to talk about it as dipole-dipole attractions. Okay, meaning you have two little magnets next to each other. The positive end of one is going to attract to the negative end of the other, right? All right, so these forces, what is an interstate? Let's get some English taken care of real quick that a lot of you probably haven't really thought about, but you've been using the whole life. Okay, so an interstate, what does that do? Does that connect within a state? Internet, does that connect within networks or outside of networks? Between separate networks. So interstates connect different states, right? So an interstate system connects the 50 states of the United States of America, right? An internet connects different networks together. And so it is a network of networks, okay? And so when we talk about forces, there's the intramolecular forces. So those were the things like covalent bonds, ionic bonds, okay? And those are very, very strong, right? When we talk about these forces, these attractive forces we've been just starting into, those are going to be the intermolecular forces. That's between molecules. These are going to, on average, be much, much weaker than the intramolecular forces like a covalent bond, okay? And you already knew this because when you boil water, does it burn the water? No, typically when you boil stuff, it doesn't change the molecule, right? And so if it was the other way around and the intramolecular forces were weaker, you'd be busting apart molecules all the time, right? And you wouldn't be able to boil things usually because they'd always bust apart, okay? You can actually see this, in fact, with certain oils. So if you've ever tried to, has anybody ever used olive oil? Okay. It has a pretty low steam point. So it has a pretty low point of boiling, actually. And you can actually see that when you use it to cook. It has like this olive oil haze over it, right? And that's the olive oil going to vapor. But it also burns at that temperature, doesn't it? And you can see some of the olive oil actually converting and blackening, can't you? And so you're actually seeing both happen about the same point. Okay. All right, so let's go ahead and look at the forces. So in terms of strength of forces, your weakest forces are what are usually called London dispersion forces or dispersion forces. Okay. Your book likes to call them London forces, which is actually wrong. That's actually not the proper way to call them. It'd be London dispersion forces or dispersion forces. One of the two. Whatever. Yeah, I used the figure from your book though, so it's easier for you to remember. All right. So dipole-dipole attractions are then going to be the next strongest. Remember when we were talking about polar and nonpolar, where it has an overall dipole? Those are dipole-dipole attractions. Okay. So you have one dipole on a molecule, positive and negative end. That's going to align with the positive end, negative end with the positive end of the other molecule, right? Hydrogen bonding. Hydrogen bonding is just going to be a very special case of dipole-dipole interaction. Okay? So it's very strong dipole-dipole interaction. That's all it is. It only happens where we have hydrogen with something extremely electronegative. Okay? Something like fluorine, oxygen, or nitrogen. Right? Ion dipole interactions. This is where you're going to have ions that are being mixed with dipoles. And so your ions have positive and negative charges. Your dipoles are then going to point the opposite charge at them and be attracted, right? And so, for example, if you have a sodium Na plus and a water, right? What will happen is the sodium is going to be attracted to that negative oxygen on the water, and that's going to be the same sort of magnetic force that you've always been seeing, right? And that's going to allow those ions to dissolve. Now, this is actually technically a intramolecular force, isn't it? This is actually your ionic attractions. So this is your ions, positive, negative, being attracted to each other, right? So that right there is the strongest one of the intermolecular forces, okay? Because when you're talking about ions, there's actually no clear distinction between which part of the ions is a molecule. So the whole crystal could be considered one molecule for the ions, or you can consider it what's called a unit cell. It's the NaCl. Okay? So when you're talking about ions, they're not really molecules. Okay? They're actually groupings of ions. Okay, so let's talk about the London dispersion forces. So these attractive forces are going to occur momentarily between all molecules. This is going to happen whenever the electrons are unevenly distributed across that molecule's surface. So when this happens, you're going to end up with a partial positive charge on one side and a partial negative charge on the other. And this is just random distribution. Notice in our room here, if we were a molecule, see how random distribution made it so you guys were uneven and did not evenly spread out? So we would have a charge if you all were electrons, right? This side would be negative, this side would be positive, right? And so if we have another molecule next to us, the electrons are going to be attracted over here, aren't they? Okay. And so that is actually a London dispersion force. We have these momentary differences in probability. They're going to happen all the time. It's fact of life, okay? If you flip a quarter and it has a 50-50 chance of being both sides, right? Does that mean you're always going to go heads, tails, heads, tails, heads, tails? Every time? No. In fact, you're actually assured to not always do that, aren't you? So you're going to go heads, 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 tails, 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 right? Okay. And that's the same thing that happens with electrons. Yeah, they want to be evenly spread out, more or less, but every now and then you're going to get built up on one side just because of random probability. 2 electrons end up this side. Okay? And that gives a momentary charge as it evens that out. And you have that happening millions of times per second. That will grab onto any molecules nearby and pull them in towards the electrons towards the positive side. And that gives you these momentary attractions. Okay, so every single compound and atom exhibits London dispersion forces. Okay? They all do. All the time. This is everywhere, all the time. So if you're ever asked a question of does this exhibit London dispersion forces, the answer is unless it's an electron or a proton, yes. Okay. Any molecular atom is going to exhibit some degree of London dispersion forces. Now, those forces may be much weaker than any other force. They may be the weakest forces you're talking about, in which case you can kind of ignore them. But they're always going to be there. Okay? All right, so this is actually called many times an induced dipole or dispersion forces. These are actually the same attractive forces as London dispersion forces. This is actually a historic thing. Typically, nowadays, they're called dispersion forces. It's very rare for them to be called anything else now, but sometimes you'll still hear induced dipole. London forces is not really a thing. It's London dispersion forces. They were talked about as a single cohesive unit originally. Okay. And so this is actually a kind of nice example of London dispersion forces. So here you have a long hydrocarbon. And so every single one of these atoms here has a chance of becoming uneven. Okay? So every single one of these atoms has a chance of the electrons building up on one side. Right? And so what ends up happening is the electrons build up on one side. It's usually not anything drastic like it's being shown here. It's usually a much smaller effect. Okay? But it's being blown up into a much larger effect so you can see it easier. Okay? All right, so what ends up happening is one of these ends up with the electrons more on one side than the other. This gives a partial negative, partial positive. This is going to pull the electrons on the other molecule next to it, and that's going to give an attraction. Okay? Then what's going to happen is these are going to repel each other, and so they all swing over this way. This is going to repel each other, so they all swing over this way. And so you get this little back and forth of positive, negative charges that matches up for a little while. Now, this is nanoseconds time scale. Okay? Very, very, very fast. It'd be very difficult for you to actually see this. Usually it's nano picosecond sort of time scales. Okay? It's unlikely you would actually be able to catch photos of this easily. Though in certain systems you can actually have been able to image it. Okay? So it's kind of neat stuff. But now, what determines how likely you are to get other probabilities? Anybody know? How many times you do it, right? If you only do it once, then you really have no chance of any other probability, right? You get heads or tails and that's it. And you're on track for 50-50, sure. Okay? If you do it twice, you're actually less likely to see the statistical improbabilities. Okay? If you do it more times, you have more chance of seeing them. Okay? And so the longer your hydrocarbons are, the more London dispersion forces you're going to get, right? And so this is why things like, has anybody know anything about cooking oils? No? How about motor oil? No? Does everybody know your car needs motor oil? Okay. Okay. So, motor oil, for example, is very long-chain hydrocarbons. And so they have very large dispersion forces. Okay? Small chain hydrocarbons, on the other hand, would have much smaller dispersion forces. So this is why, for example, propane is a gas at room temperature. Versus if you look at gasoline, which is like an octane, right? 8 carbon, that's actually a liquid at room temperature mostly. Right? And if you start looking at diesel, that's a liquid at room temperature. You go longer, you can start getting liquids even at high temperatures, which is what your oil in your car is, non-synthetic oil in your car is. And then if you go even longer, you can get things like the what you would see in an asphalt. Anybody know how they make asphalt? No? Nobody knows? Okay. Wow. Okay, so there's something called a fractional distillery. Okay? What they do is they heat oil, and then the different fractions are going to go up a long pipe and come off at different points. Okay, so the very light stuff is going to make it all the way to the top, and it's going to come off or get burned, one of the two. And that's your things like methanes, ethanes, propanes, that sort of stuff. Okay. And then the next layer that comes off is going to be things like your butanes, right? Like your lighter fluid. Okay. And then your next things that come off is going to be things like gasoline. And then you're going to have diesel that comes off. Then you're going to have kerosene that comes off. And then much lower, more towards the liquids, you're going to have things like your motor oil coming off. Okay. And the stuff at the very bottom that gets left behind, that's actually what they make asphalt off of. Okay. And so it's just a liquidy at high temperatures. It gets a little liquidy. But at room temperature, it's actually a solid. It's kind of rubbery. Okay. And they take that, they pour it in with a bunch of rock, and that's actually how you get asphalt. You layer it out. Anybody ever seen asphalt on a really hot summer day? If you put your bike stand, so you're riding a motorcycle and you put your kickstand down, anybody know what happens if it's over 120 degrees Fahrenheit? Your kickstand actually punches a hole through the asphalt. And you come back and your bike's on side and you gotta work your kickstand back out. It's actually quite funny. That also can happen with, you can leave lines in the road, or you can actually put down heavy objects and it'll put like little lines. It's actually really funny because you see like a lot of quarter imprints because people put down change and drop it, and then people put rest cars on it by accident, and it imprints the coin into the asphalt. Okay, so that's actually London dispersion forces. All of those are. So the best way to think of London dispersion forces is that individually London dispersion forces are the weakest of the intermolecular forces, okay? But think about them like strings, okay? So if you have a one string on you, are you being bound tightly? No. No, you can snap that pretty easy, can't you? Okay? But what happens if you have 1,000 strings, like Gulliver's Travels? Anybody seen that book or movie? No? Sad. What happens if you're wrapped up by thousands of strings? Are you going to be tightly bound? Yes. Yes. And so London dispersion force is one of these, not much of a force. Two of these, still not a lot. 10, 20 of these, a lot more, right? You've really qualitatively changed it at that point. Okay. So again, that's London dispersion forces. Now, let me ask you a bit of a logic question. See if your logic cells are still working here. If you were wrapped up, you had a string connecting one of your fingers, and then somebody put a giant rope on you, which one is more threatening to you being able to leave? The string or the rope? The rope, right? So if you were talking about what is causing this to have a higher boiling point, what is causing this to not melt as fast, then the stronger forces are the things you need to worry about first, right? And then you could worry about London dispersion force, okay? Okay, so typically speaking, the dipole-dipole attractions are going to be much more important. If I ever give you a question of which force is being exhibited here, and I give you something like something polar, like a OCH2, then it's going to be the dipole-dipole attractions. Yes, that has London dispersion forces, They all do. It's just not as strong. Okay? It's just not as important. Okay, so again, dipole-dipole attractions are going to be polar molecules. They're going to have permanently uneven distributions of electrons, and so you'll have one positive end, one negative end. These are permanent dipoles, and so you get dipole-dipole attractions between those two dipoles, just like little magnets, because they are little magnets. This type of interaction is going to involve the interaction of two dipoles. Again, it's always denoted as dipole-dipole attraction. Remember that London dispersion forces are always in everything when you're talking about all the atoms and molecules. So they're still going to be here. They're going to be in all the rest of them. They're just not very important compared to dipole-dipole attractions, okay? In most cases. All right, so these are dipole-dipole attractions. We can see here again, we have an oxygen versus a carbon, right? And so this has a permanent dipole where this side is negative because the oxygen's going to pull the electrons over there. This side right here is positive because the carbons don't have as much electronegativity. They don't hold on to those electrons as well. Everybody okay with that so far? Okay. And just like if you'd taken a bag full of magnets, anybody ever like stored fridge magnets and had to remove them and put them on the fridge later? Kind of like that, okay? If you ever had magnets, a bag of magnets, or a container of magnets, you would see the same pattern, right? Where they arrange themselves in a nice positive, negative, positive, negative, positive, negative, right? Okay. Okay, and that's what we're seeing in dipole-dipole forces. So hydrogen bonds, these are just going to be very special dipole-dipole forces because they have a hydrogen with something very electronegative. So hydrogen bond is going to involve a polarized hydrogen, that is a hydrogen in a polar bond, i.e. it bound to be something like oxygen, nitrogen, or fluorine. And this is then going to be able to make a much stronger connection because that little hydrogen is going to be able to fit much closer and experience a lot more negative charge and be pulled much tighter, okay? And so these end up being much stronger attractive forces than your dipole-dipole attractions typically. The important thing about a hydrogen bond is it requires a hydrogen bond donor and a hydrogen bond acceptor. So a hydrogen bond donor is going to be a hydrogen that's attached to an oxygen, nitrogen, or fluorine, okay? So it has to have a hydrogen attached to an oxygen, nitrogen, fluorine. Does this have a hydrogen bond donor? Is there a hydrogen attached to an oxygen, nitrogen, fluorine? There is not, is there? There's just an oxygen, but it's only attached to carbon. There's hydrogens, but they're only attached to carbon, aren't they? Yeah. So this does not have a hydrogen bond donor, okay? What it does have, however, is a hydrogen bond acceptor, right? Which is a lone pair on something electronegative, like an oxygen, nitrogen, or fluorine, okay? And so this part right here, these lone pairs on oxygen here, those are actually hydrogen bond acceptors, okay? All right, so right here we see an example of something that does hydrogen bonding. Are you surprised that's water? Yes? No? Yeah, kind of obvious that was going towards that since I kept doing oxygen first, right? Hydrogen with oxygen, hydrogen with oxygen. So water, you see here that has hydrogen attached to an oxygen, actually has two of those. And so water actually has two hydrogen bond donors right there, and it has two hydrogen bond acceptors. This is actually what makes water's crystal structures. So you know how a snowflake makes like a hexagonal structure? Whenever you cut snowflakes when you're a kid, you always do them in hexagons, right? That's actually why. Is that these arrange in little triangular hexagonal structures. Okay? And it's actually because of the geometry of this hydrogen bond here. Okay, and so again, we have that partial negative charge here. We have the partial positive charge here. This is the hydrogen bond donor, the hydrogen bond acceptor right there, the lone pair. Okay? And those are making hydrogen bonds. These are very strong intermolecular forces, and this is why water, for example, boils at 100 degrees Celsius, which is actually pretty high, isn't it? Okay. Anybody know where the largest use of energy in human culture actually is? Largest use in industry, largest use in private, largest use period of energy, of electricity, or really any form of energy. Heating and cooling water. That's the majority of the energy usage on the planet. Okay? By nature and by humans. So, interesting little factoid. And that's all because of hydrogen bonding. If hydrogen bonding isn't so strong, we wouldn't need as much energy to heat it, would we? Okay? And it wouldn't take as much to boil it. You know that all power generation actually is steam generation, right? You guys not know that? Okay. So ultimately, all power generation is actually steam generators. We heat water to boiling. It pushes a little fan, steam generator. That generator converts that energy to electricity. Right. So this is hydrogen bonds right here. It can be between the same molecules, but you can also have different molecules. So for example, this would be your isopropyl alcohol. It's dissolved in water, for example, or ethanol, one of the two. And so you can actually have, for example, water, hydrogen bond to this isopropyl alcohol, or you could have ethanol mixed with isopropyl alcohol. And these are all miscible, meaning they can mix at any amounts. Okay? You already kind of knew this because ethanol's the alcohol that people drink, right? And so you can actually have drinking alcohol that comes in 30%. You can have it come as 50%. You can have it come as 70, 80, 90. You can be 99% ethanol and 1% water, right? Or you can be 99% water, 1%. Okay? And that's because they're miscible. They can mix in any quantity. Okay? All right. And so this right here is some other cases of hydrogen bonding again. This one's actually an internal hydrogen bond within the same molecule. So you have a molecule that actually wraps back around and the hydrogen bonds to itself in this case. Over here, we have water hydrogen bonding. Notice this one's only a hydrogen bond acceptor. The water is the hydrogen bond donor here. Okay? And so this does undergo hydrogen bonding with water, right? But on its own, this molecule cannot do hydrogen bonding. Is that making sense? Because notice again, we have no hydrogen off in oxygen, nitrogen, or fluorine. All right, so these are some different hydrogen bond donor acceptors. This is actually ethanol right here, by the way. So this is water with ethanol, and that would be like beer, wine, vodka, whatever. Okay, so ion dipole interactions. So on one side, you're going to have your ion. The other, you're going to have your dipole. And so, for example, we have sodium chloride, which is table salt, right? And when we mix table salt with water, those two actually dissolve, right? So we dissolve our salt into our water. And what's happening here is the sodium ions are going to be separated from the chloride ions. And the waters are going to build a little sphere around those sodium ions. They're going to do so by the negative oxygen side being attracted to that positive sodium right here. Okay? And they end up with a little sphere. This is called hydration, as in putting waters around it. The chloride, which is negatively charged, is going to end up with the positive hydrogens being associated with it, attracted to it. And it will end up with a little sphere of water molecules, which gather around that. And so that will then be a hydrated ion. Those will be separate, floating around in solution. Okay? And that's how things dissolve, actually. And these forces, these attractions, are going to be ion dipole attractions that do that. All right, so let's talk about ionic attractions. When you have oppositely charged ions, they are going to attract each other. So an ionic attraction is actually going to be individually the strongest of the attractive forces. Ionic attractions are sometimes called salt bridges. This is what is referred to an ionic bond. this is very old terminology that has heavily been discouraged now, which is salt bridge, because there's a whole nother thing that's a salt bridge in chemistry. Okay. Um, but your book brings it up, so I do need to mention it. So I highly recommend you call this an ionic bond and don't call it a salt bridge. Okay. Salt bridges are actually something that exists in batteries, and they're a whole different thing. All right. So organic functional groups, we have our carboxylate ion. Right here we have that protonated amine, or an amine salt. And so this would actually be the sort of thing you would see in amino acids. So if you were to put amino acids, you notice they're a solid whenever you buy amino acids, right? They're actually crystal form. And this right here is that crystal. That's ionic, right? And so you have ionic bonds between the carboxylate and the protonated amine. Okay. Anybody have any questions about that so far? What do you notice about salts, by the way? So how many of you have melted or boiled water? Everybody, right? How many of you have melted or boiled something like a like oil? Everybody? Butter? All melted butter, right? Okay. Okay. How many of you have melted or boiled something like propane? Butane? Nobody? Nobody's used a lighter? You've used a lighter, you boiled butane. Okay. So everybody's seen those. Now, how many of you have ever seen boiled NaCl, table salt? Anybody? Thank God, because it happens at like 1,000-something degrees Celsius. You probably would have died from it. Okay? It's extremely hot. Melting salts is actually usually in the 500 plus degrees Celsius range. So it's incredibly hot. It's very, very hard to break up these ionic bonds with heat. Okay? So that's why none of you have ever seen any salts melted or boiled, actually. You may have seen amino acids. You can actually melt amino acids, but unlikely because it's actually fairly high temperature, and usually you end up reacting if you're not careful. Okay? So most of you have probably never seen those. Now, this right here is going to be a little table, and so this is sort of a guide to figuring these out and which one it is versus the attractive force. So the first sort of question you want to ask yourself whenever you're going, what sort of forces will this experience, is does it have a dipole? Is it a polar compound? One positive side, one negative side. Okay. If it's polar, then it's going to have other forces than London dispersion forces. Okay. If it's non-polar, then it's only going to have London dispersion forces. You don't have to worry about any of the others. Okay. Now, the next question is hydrogen bonding possible? Does it have a hydrogen bonded to an oxygen, nitrogen, or fluorine? Okay. If it does, then you're going to have hydrogen bonding available. If not, you're only going to have dipole-dipole forces. Okay. Because it's polar but doesn't have hydrogen bonding available. All right, so let's say that hydrogen bonding is possible. We have a hydrogen with an oxygen, nitrogen, or fluorine, right? So, does it have an ionic charge? Does it have a full charge on these things? Okay. Does it say plus or minus on that charge? Okay. One of those two. If it says a charge, if it has an ionic charge that's present, then you're going to have to worry about ionic bonding, right? If not, then you're hydrogen bonding. Okay. So let's say we have a charge, right? Is ionic charge present? Yes. Are the opposite ionic charges present? Do we have the positive and the negative? Okay. If we have the positive and negative, you could get ionic bonding. If we only have one of the charges and then we have a dipole, something with a dipole for the other ingredient here, that's going to end up being ion dipole. attractions. Okay? And that's mentally how you go through this. Now notice that after you practice this a bit, this is going to be very, very fast, and you'll be able to do this very quickly. Okay? All right, so let's predict some vapor pressure and boiling points for some alkanes. So remember that alkanes are going to be nonpolar. That means the only attractive force they're going to experience is London dispersion force. Okay? So a molecule with a large surface area is going to have more contact, more electrons that are going to interact, and so it's going to have larger London dispersion forces. Straight chain alkanes are going to have more contact. They're going to have more surface area. Everybody familiar with surface area from biology? Same sort of concept. So if we have something like pentane, for example, and then we have over here octane, they're both straight chains. So octane is going to have the larger London dispersion forces, right? Okay. All right. And right here we see some examples, and we go from methane up to decane. And what you can notice is the boiling points, for example, for methane, ethane, and propane. These are all negative, right? And so you always see these as gases, don't you? You've probably never seen these as liquids. Okay. Butane, though, you've probably seen as a liquid when it's under pressure. And that's what you see in a lighter. So if you anybody ever refilled a lighter? No? Okay. Has everybody seen a lighter? Been at a gas station and seen lighters? Okay. Or have actually held one? All right. Okay, so if you look at those lighters, there's a little tank, right? That little tank has a window so you can see into it, and that's actually pressurized butane. If you hit the lighter, strike it, that little end cap that you can push down, that actually lets butane out. And it comes out as a gas, doesn't it? Okay. And so that's the butane right there. This right here is the pentane, hexane, and heptane, and octane. These are the fragments that you typically find in gasoline. Okay. And these up here are the sort of fragments you would typically find in something like diesel. And that's why, for example, if you go to the gasoline pump, you actually see a haze of the gasoline as you're pumping it, but most of it stays as liquid. Okay. That's because the boiling points are actually well above room temperature, aren't they? But you got some stuff that's kind of close. And so a few of that molecules can escape to vapor. All right. So let's look at branched. So straight chained is going to have higher boiling points than similar molecular weights that are branched. One of the things you want to keep in mind is the more molecular weight you have, the more electrons you're going to have. And so typically dispersion forces go up as your molecular weight goes up. However, if you branch the alkanes, this is going to give you less surface area to be attracted across, right? And so you effectively have isolated some of your molecular weight, some of your electrons, and so you get lower dispersion forces. Okay? And we can see the difference here. So for example, this is hexane, this is your dimethylbutane, and you can see because of the branching, we have actually went down by about 11 degrees Celsius for those boiling points. That's how much that's affected those dispersion forces. Okay? Let's talk a bit about melting points. So melting points are going to have the same exact trend as your boiling points. Stronger and more numerous forces between the molecules, you're going to have a higher melting point. What you can think of as melting points is breaking 20% of the connections to get melted. To go to boiling, we have to break all the connections, right? And so it's the same trend, just boiling is a bigger example of it. Okay? All right, so let's predict these points. So number one is determine the strongest attractive force that's present in each of these. Number two is predict the lower vapor pressure and the higher boiling point. You're going to base that on the strength and numbers of forces present. So for example, does it have dipole-dipole forces? Does it have London dispersion forces? Okay. And then, is its London dispersion forces, is it a long straight chain? Is it something short? Okay. And that will tell you the attractive forces between them. So let's talk about the attractive forces that keep your biomolecules in shape. Has everybody heard of a cell membrane? Yeah? I'm like actually asking this, okay, because I can't actually assume that, right? Okay, so what cell membranes are is they're actually lipids that have polar heads, okay? So they have nonpolar tails, which exhibit London dispersion forces, right? And on the top of them, then they have something that exhibits hydrogen bonding, okay? And so what you get is the nonpolar tails all point towards each other in a lipid bilayer, meaning you have two layers of nonpolar tails pointing into each other. On the surface, then, you have things that do hydrogen bonding, okay, which are going to be the polar heads. So one of the best ways to sort of think about this is if you think about them as little magnets being water, right? Those are the water, hydrogen bonding, and dipole-dipole interactions, okay? And then you have the other side, you have more something like a Legos, right? That doesn't have magnets in it, okay? And so if you have a stronger force that's connecting things very strongly, what happens to all the stuff that doesn't have magnets in it? It all gets pushed out, doesn't it? It gets excluded. And that's what happens when you mix oil and water, right? So when you have water, they're all little magnets, aren't they? They're all going to attract together, snap together, and all the oil particles then are going to get pushed out to the surface, right? And they separate in two layers. Okay, so this is actually how your biomolecules are held together. This is how you get structures of your biomolecules. This is how your proteins get the structures they have. This is how your DNA gets the structure it has. Those are all intermolecular forces, actually, that make those structures. So, for example, the cellulose molecules are going to be held tightly together. This is actually going to be done through hydrogen bonding between neighboring molecules. Your London forces are actually what hold your cell membranes together. And so you have these long nonpolar tails that are going to associate, and that's actually what holds that cell membrane together. You may not know this, but your cell membranes are actually semi-liquid, okay? They actually constantly flow around. And everything that's embedded in them moves around because they're semi-liquid, okay? London forces, actually, hydrogen bonding is going to be what holds the DNA double helix in that twisted pattern. That's actually what causes that twisted pattern. There's actually some London dispersion forces as well. I'll show you a picture in just a second. Protein structures are actually going to be held together by a pretty interesting combination of these things. So you'll get London dispersion forces, which holds a portion of it together. Then it's going to wrap around to hydrogen bonding, which will create the shapes, and bring it back to London dispersion forces that holds another part together. Okay? And it's a complex interaction that makes that shaping. So right here we see DNA, right? And so what you see is these matches right here, which are between your bases. Everybody's familiar with your bases matching up in DNA? Okay. ATGC, right? Okay. And so this right here is actually that matching. That's a G and a C. You can see it matches 3 hydrogen bonds. And that's how actually the bases hold together. How it determines GC matches is because it has 3 hydrogen bonds, which match up in the correct order. AT, on the other hand, has 2 hydrogen bonds, and they match up in the correct order. Okay? If you tried to do the other one, hydrogen bonding wouldn't match. And that's the key part of that DNA. Okay? Now, the other part that actually holds it in this structure like that, where it's that twisted spiral effect, the double helix effect, is actually, see how these right here have pretty large chunks of them that are flat and have lots of electrons? So these right here that stack on top of each other actually exhibit London dispersion forces. So that stacking like this actually is your London dispersion forces matching up. Okay? And so that's actually what is causing this stacking where it's rotating. Anyways, kind of interesting stuff, I think. All right, so that's your DNA. Let's talk about a bit of golden rules of solubility. So like dissolves like. That's usually the easiest way to remember this, okay? Things that have similar interactions will dissolve in each other. Things that have different interactions are not going to dissolve into each other. Okay? And so oil and water, these don't mix, but sugar and water do. Why is that? Well, water has hydrogen bonding, right? Oil has dispersion forces only, right? And sugar has hydrogen bonding again, doesn't it? So sugar and water mix because of hydrogen bonding. Oil and water don't mix because the water has hydrogen bonding. It's going to squeeze the oil out. Okay. All right. So again, we exhibit solubility in both cases or lack of solubility in the oil and water case. Your maximum amount of substance that can dissolve in a specific amount of water is actually at a given temperature. This can be called a substance solubility in water. There are solubility measurements in every solvent you can imagine. For example, ethanol, methanol, hexane, anything you can imagine. Okay. And so the golden rule again is solubility of like dissolves like. Okay. Just remember like dissolves like, and you're going to have a good interaction with these. Okay. You can mostly get it. The similarity is going to be if the molecules are polar or nonpolar, if they exhibit hydrogen bonding, if they do not. Okay. The most important one is polar and nonpolar. So, for example, oil is nonpolar, right? Water is polar. Sugar is polar. All right, so again, similar polarities are going to participate in the same types of attractive forces, and so they're going to dissolve into each other. They may not dissolve incredibly well. They may not be miscible, but they'll be able to interact, okay? And that means they're going to be soluble to some degree. The terms hydrophilic and hydrophobic are going to be a little bit more easy to deal with than polar and nonpolar because they actually tell you in terms of water done. Okay? And so most of you are going to be more familiar with hydrophobic, hydrophilic. Hydrophobic means it is water fearing, right? Hydrophilic means it is water loving. Okay? So something that's hydrophilic means it dissolves in what? What would hydrophilic substance dissolve in? Water. Does it dissolve in oil? No. Hydrophobic, water hating, right? So if you're hydrophobic, are you going to dissolve in water? No. Are you going to tend to dissolve in polar molecules? No. No. Are you going to dissolve in nonpolar molecules? Perfect. Perfect. Okay, so nonpolar compounds, of course. Oils are going to be attracted to neighboring molecules through London dispersion forces. Water is going to be polar. It's going to act with other substances through dipole-dipole interactions, hydrogen bonding, and ion-dipole attractions. Oil and water are typically the stereotypical on-like example because they're the most familiar one. Okay? The attractions among water molecules are much greater than the attractions between the water molecule and the oil molecule, and so the oil molecules get pushed to the side, the water molecules all snap together, and you end up in an exclusion, okay, where the oil ends up getting gathered away from it. All right, so this is some different polar molecules. So again, the hydroxyl groups is a very stereotypical hydrogen bonding polar molecule, okay? And so this is one of the ones you'll be most familiar with. This is actually your table sugar here mixed in water. And so you can see that there's quite a few hydrogen bonding groups here, right? This one's only a hydrogen bond acceptor, but the rest of these are both donors and acceptors. Okay. And so water dissolves sugar pretty well, doesn't it? Okay. May take a little while. You may have to mix it in heat, but dissolves quite well. And that's why, for example, you start drinking soda and sweet tea, and it's just massive amounts of that are actually sugar, isn't it? You know, they're like 30 to 40% sugar. Because it dissolves too damn well, doesn't it? Yeah. Ionic compounds. This is your ionic compounds. Remember, I was talking about those little hydrated ions where you'll develop spheres of the water around the ions. This is actually how you get table salt to dissolve. So what happens is you put your table salt crystals in, and that's these right here, right? Any ones that aren't dissolved and stay as table salt crystals are still like this. And so what's going to happen is the water molecule is going to come to the edges and they're going to be attracted to the ions. They're going to start pulling those away. Once you pull them away, you'll develop a shell of water molecules with the positive side attracted to the negative ion, the negative side of the water molecule attracted to the positive ion. And these little shells are going to float around the solution, and that's how the dissolved ions are actually dissolved. Okay? And so that's dissolved table salt. This process is actually called hydration, and it actually takes quite a bit of energy to break these ions apart. This is why it can actually take a very long time to dissolve salt if you throw it in water, right? And one of the ways you can speed that up is you can heat it. Okay, so ion-dipole interactions actually increase drug solubility. So about 85% of all drugs are actually going to be administered orally. This is to be absorbed in the digestive tract. That means that these drugs actually have to have a pretty good water solubility, okay? And they need to be made soluble in water. Now, you may notice that most drugs, if you actually look at their chemical formulas, are like really large hydrocarbon molecules, aren't they? They're not normally soluble in water. So more than 40% of the new chemicals discovered by pharmaceutical industry as potential therapeutic agents are actually insoluble in water. And thus, you can't give them orally, you can't give them as tablets, and they never really make it into the drug market. Okay? It's actually quite a difficult process to go from discovery of something that works, if you can administrate it, to something you can actually administrate. Okay? So pharmaceutical companies typically try to create molecules that have amines or carboxylic acids in them. At the pH of the body, this actually gives you a charged form, which will be a salt form. It'll be an ionic form. Okay? And this is going to increase the molecule's solubility in water, and thus the person can take it as a pill, and then they can have it dissolve in their bloodstream and distributed throughout their body. So the ion-dipole interactions increasing your drug solubility. For example, right here, we actually have an example of this. So right here is a amine, but it's not quite soluble enough. So if we were to try to administer this drug right here to a patient, it would actually not distribute through their blood. Okay? They would end up pooping most of this out. Okay? And so what we need to do then is we would add HCl. So this is actually Sudafed. That's that nasal spray. And so they add HCl to this mixture, just enough to acidify all these molecules right here. And that gives us the pseudoephedrine hydrochlorine. Okay? You may actually recognize this because it typically has the name here, a dot, and then HCl. If you look at the back of the package, that's probably what you're going to see. Okay? And so now this right here is an ion, isn't it? Everybody said okay? And so that's going to increase the solubility because ion-dipole interactions are stronger interactions, aren't they? Yeah. By the way, that's the exact same thing that's done between crack versus cocaine, in case you're curious. That's the exact same thing that's being done there. It's just a very common method to make a drug more soluble in your bloodstream and thus have a more potent, faster effect. Okay? This being a good use of it, the crack cocaine being a really bad use of it. Okay. So this is amphipathic compounds. This is going to have a bit of both. So fatty acids are mostly hydrocarbons. They're mostly a long carbon chain here, but they have a carboxylic acid group. And so these are amphipathic, meaning you have part of it that is hydrogen bonding, and part of it over here is only London dispersion forces, right? Or another way of saying that, this part here is polar and is attracted to water, isn't it? This part here, nonpolar, not attracted to water. Okay. And so amphi means both. Pathic actually means condition. So under both conditions, you can have some degree of interaction and some degree of solubility. Okay. And this is why fatty acids are actually what compose your cell membranes. Is they have this part here, the nonpolar part, come together, and that composes the inner part of your cell membrane. This part here composes the outer part. Note that you actually also have this right here is actually going to be in the COO negative form, where we've lost the hydrogen, the H plus. Okay, and so it's actually an ion dipole interaction. So let's talk a bit more about amphipathic compounds. We have soaps. These are going to be composed of fatty acids that we have actually converted to salts to make them more soluble. And so soaps are going to be ionic because they contain carboxylate, which is the hydrogen has been removed here. We've removed an H plus, and so then that's negative oxygen there. And so the charge on the carboxylate is going to make that a molecular ion. That's going to make it more soluble. And so what you end up getting is the nonpolar tail is going to associate with things like grease, nonpolar substances, right? The polar heads, on the other hand, the ionic heads, are going to end up associating with water. And so it allows you to surround your grease molecules with your soap molecules, have the polar heads all pointing out towards the water, and then that dissolves in the water to lift it away. Okay. So let's look at pictures of that real quick. So this would be a cartoon representation ball and line structure. This right here, your nonpolar tail. This right here, your polar heads, right? For your soap molecules. So if you're looking at this in terms of what it would do to grease, all these nonpolar tails would stick in grease. And so you'd have grease surrounded by these sticking within it. And these polar heads here would all be pointing outwards. So you can then associate with the water. So you can do several things with them. Soap actually is going to form what's called a micelle. You also form micelles within your body as well, not just soap. Okay. And that's where you have a single layer, not double layer. So all the tails just point inwards, and the heads all point outwards. And so the polar heads will form a shell. That's going to be the shell of your micelle. And that's what that looks like right here. So here would be something like soap, right? Within here, this would be a nonpolar center. You could have something like grease here, but this would also be the soap molecules in general. Okay. And then you have the polar heads out here, and they're going to associate with the water all the way around. Can everybody kind of see that as a three-dimensional structure? Okay, and that's a mice. Okay. You'll notice it's very similar looking to the lipid bilayer of your cells. No. Okay. The only difference is you'd have another layer that points toward the inside there. Okay, and so again, that golden rule, you have soap, it's going to associate the nonpolar side with the nonpolar grease, the polar side with the water. It's going to help you lift off the water into the polar solvent we call water. This is actually what's called an emulsifier, and that's because when you add the soap, it's going to create an emulsion. Okay, anybody ever seen a salad dressing? Okay, so if you were to take just oil and water and mix them really hard, very temporarily they'd mix together, right? And then they'd separate pretty fast. Okay, and that's typically what's called an emulsion. That's like salad dressing. That's why the salad dressing separates out what you're eating. If you were to go ahead and put soap in there, it's going to partially emulsify and partially it's going to create what's called a colloid. Okay, colloids stay suspended for longer. You'll notice they look like milk. Okay, and that's because milk is also a colloid. Okay, so let's predict the more soluble substance based on the overall polarity of the entire molecule. So here we have vitamin C, ascorbic acid. Here we have vitamin E. And so which one do you think would be more polar, more water-loving? What do you notice about this one? Big nonpolar tail, right? Okay. What do you notice about this one? Completely surrounded by polar groups, isn't it? Okay. And so vitamin C is going to be very hydrophilic. Okay. In fact, you will urinate out almost all your vitamin C every 2 days. Okay, because it is so hydrophilic, it's going to stay in water all the time. It's going to move with your water. Okay, so you always have to get more vitamin C all the time. Vitamin E, on the other hand, is actually fat soluble. So it doesn't dissolve in water very well. And so you only need it like once a week or so. Okay. If you got it once every 4 days, you're good. Because you'll be able to keep it in your body. The water won't rinse it out. Okay, so fats are solids, oils are liquids. Fats are going to include things like steaks, lards, butters. They're typically derived from animals. Oils are going to be the liquid form, non-polar compounds, and those are going to be things like what you get from corn, soybeans, and peanuts. These are typically derived from plants. Both the fats and the oils actually belong to the same class, and that's hydrolyzable lipids. These are called triglycerides. The big difference is the presence of double bonds and the lengths of your chains. Okay? So determining a fat versus an oil is as simple as examining the physical state of your triglycerides as room temperature. So if it's a solid at room temperature, fat, right? If it's a liquid at room temperature, oil. So if we compare these, what are we going to get the difference being? It's going to be how well do they line up? So how much London dispersion forces do they exhibit? So right here, we actually see a fat. And we can see that these actually line up quite nicely, don't they? A little bit, not perfect, but pretty nice. We look down here, and what we notice is these all have kinks in them, don't they? And so they don't line up nicely. They don't stack nicely. And so that ends up being an oil at room temperature because of those double bonds. And that ends up having smaller dispersion forces to break, right? Thus, liquid at room temperature. This has larger dispersion forces to break because it stacks nicer. And so that ends up being a fat at room temperature. Okay? All right, let's talk a bit more about dietary lipids here. Notice, by the way, we have a polar end right here once we free that of that glycerol. Okay? Right now, it doesn't have any polar end that's available to do most of the hydrogen bonding because this glycerol right here is in the way. It's actually what we do when we add NaOH to make our soap. Okay? It frees it and ionizes it. All right, so does anybody have any questions about that so far? Okay, so notice that those double bonds tend to put a kink in that chain, don't they? And so they don't stack quite as nicely. Okay? That also restricts those molecules so they can't flip-flop as easy. That double bond is going to hold them in that position. Okay? So if we look at our oil molecules, we're going to notice that we're going to typically have unsaturated cis carbon-carbon double bonds in our hydrocarbon tails, and these are going to make it polyunsaturated. So the cis double bonds in those tails is going to create that kink because the cis bond ends up on the same side, right? And so you end up with a kink to the tail. Okay. These kink tails are going to interact less through London dispersion forces. They don't stack as nicely. And so they're going to have lower melting points, lower boiling points. Okay. Bless you. And that's going to mean they also tend to pour easier. So you get more liquid-like behavior, more easily pouring. Versus if you have better stacking, it's going to have more resistance to pouring. Okay. That's why cooking oil that you usually use pours easier than like gasoline oil, which is much thicker, right? Oil for your car. Okay, and so if we look at our phospholipids, this is actually the main structural components of your cell membranes. These are your phospholipids. These are going to have a glycerol backbone, just like the fatty acids. The big difference, again, it's going to have an ester linkage. Your big difference here is it's only going to have 2 fatty acids on that glycerol backbone. The third part, where it would have the third connection, is actually where the phospho group is connected. Okay, and that's what makes it the phospholipid. Now, that phosphate group is going to contain an ionic part, and that makes it highly polar, right? And so it increases the polarity of its head. making it very like a soap molecule that has two tails. Okay. The fatty acids tails are going to be your nonpolar part. And so that right there is your phospholipid. So here's your fatty acid tails, right? Here's your glycerol component. And this is actually the inorganic phosphate head right there. And so that's that charged component that's going to make it more soluble on this end. Okay. More water soluble. This is an abstraction, so you can look at it easy. Okay. All right, so if we look at the phospholipids, we're going to notice that there's many different phospholipids. They're all going to share a very similar structure, though. They're going to have a glycerol backbone, two nonpolar fatty acid tails, which can be very different fatty acids, depending on what you eat, really. And they're going to have the polar phosphate-containing head. So your two tails, your phospholipid, actually are going to affect your overall shape of your molecule. So can you stack elements of two as easy as you can stack individuals? No, you have to do different angles, don't you? And so if you have two tails, that's actually going to spread that angle out on what you can make for a surrounding membrane. Okay? And that's actually why phospholipids generate lipid bilayers, because it has to assemble very broadly, very large. Whereas a mycel only has one-tailed members, and so it can assemble very tightly. Okay? All right, and so your phospholipids assemble in a cylindrical shape. It's going to have a much larger head group. It's going to hinder their ability to form micelles because of these large tail sections. And so your cell membrane is what you're going to see, which is a lipid bilayer. Okay? If it's not a cell, it'd still be a lipid bilayer. All right. And so, again, you'll see that the phospholipids can't exist as a single layer. They're going to form bilayers. Instead, you're going to have the phospholipids with bilayers, the polar head directed towards the outsides of that bilayer, and the inside towards the cell. And so if you arrange these, you're going to get this right here. So see the double tail of the phospholipids. So the non-polar ends are all going to arrange together with the polar ends arranged towards the outside. And this is going to make a complete three-dimensional structure. Is everybody okay at that part? Fantastic. Remember that it's going to be aqueous up here. It's going to be aqueous down here. So this is going to be water on both ends, and this is just going to extend out. Okay. Okay, we will start up here next time. You all have a great day. I'm going to go ahead and end 2 minutes early. So I don't want to start in fluid mosaic.